consider this problem, right? Because in modern days research, solving problems is one thing, but computer science is expanding rapidly. I think how we approach a particular problem itself probably is a good experience as well. So about 15 years ago, I think this didn't work. I will just use my hand right now to do here. So about 15 years ago, yeah, I need to click on here. That's fine. Yeah. So 15 years ago, we had a new colleagues, young faculty, just came to USC. You have to think about 15 years ago. So the conversation is of that time. And so he's rising star from in convex optimization, which is important to the storyline, and in game theory, computational game theory. And I think he's Tim Rothgarden's first ever PhD student from Stanford. And when he joined our department, I took him out for a short walk on campus to get coffee and so on. And so I asked him a very simple question. You know, when you walk, you ask short questions. I asked him, today you never ask this question anymore. Maybe ask something about, you know, larger language model, right? But, you know, do you know anything about machine learning? And Xiaoling is a very, very direct person. And his answer is very short, said, not even a bit, right? So at that time, I was not totally sure what to ask next. And I just also confessed that I know nothing about it, right? So this, you can see some picture on the campus right now. And then he began to say something which I think is very deep, you know, even in this short conversation. And he just said that I actually don't know any of the basic words in machine learning. I said, but this sentence is easy to follow up. You simply just say which word, right? So that's essentially I ask, you know, give me an example of a word that you don't understand in machine learning. And he thought for a while, and he said one thing deeply surprised me. He said regularization. And so clearly, to me, it's surprised because he's an expert in convex optimization. And regularization is everywhere in convex optimization. So clearly, it doesn't mean that he didn't understand the definition of regularization, what they look like. And I think his answer is much deeper, is that he didn't understand how regularization mathematically or theoretically is connected with learnability, right? Even though he knows everything about regularization in every possible way, but he said, I don't understand it because I don't quite see the path to explain learning. Right? So this is a much deeper question. And it's a great way to start research, right? Because in modern days, research is very much curiosity driven. If you don't understand, you want to take a simple step to see whether we can understand the problem. Right? So what is regularization? Regularization is widely used in machine learning. Mostly is used to overcome overfit, right? Because modern day data-driven machine learning is basically try to convert a model selection into an optimization problem. Right? It has a loss function, objective function to optimize, to fit observed data. And the hope is that by fitting the data better as optimization, you're able to arise a model that can generalize. Right? So that's essentially the framework of machine learning at a very high level. However, theoretically, this notion called empirical risk minimization, namely choose the best model for the data, can overfit, right? Namely, it tailor too much into certain unnecessary features and details of the observed data. And therefore, in practice, people often introduce this notion called regularization to soften out or make it more robust. There's many different ways to model it of this optimization-based learning process, and hopefully make it more robust for future generalization, right? So that's essentially the basic role of regularization. And so it's also tied with a very beautiful principle in learning that is called outcome research, right? Because outcome research essentially try to promote the simplest model to explain data, right? Just like, we are mathematically driven. We like simple proofs. We don't like a complicated, unnecessary proof, right? Simple proof somehow are more intrinsic. So this is very much aligned that philosophy. That is the simple model that can explain are the best model, right? So this outcome research. And so once we put into this picture, two of us finally got our coffee, and then as a theoretician, the best way to take a step about something you know nothing about, right? But you're curious about is to make a conjecture, right? It doesn't matter how good the conjecture is. It doesn't matter whether the conjecture is right. But if you're able to make a small conjecture, that will guide your thought process. And even though this conjecture is utterly wrong, and the fact you're able to realize utterly wrong, you will make progress, right? So we make livings of both the counterexamples and the progress. So this is one of the basic steps. So essentially in regularization, the basic framework, if you think about outcome research, is to try to minimize a training error, also combined with model complexity, right? Intuitively, you want to make a simple model that explain. So along this direction, what can we ask as a theoretician know nothing about regularization is to use our very basic principle to see is anything learnable that can be learned by structured risk minimization. Namely, is regularization a universal learning platform, right? So this is naive, but if you follow the fundamental computer theory principle, right? We have NP completeness, we have this all usually called universality. And the question here is regularization is a universal platform, at least for some general class of learning, right? So this is how basically we started that to as our first question to understand this basic concept. And so if this happened to be true, at least we justify, this is a reasonable question. If it happens to be true, at least it's our way to give us some kind of proof that the outcome research is a good principle, right? At least give some kind of notational similarity to that widely believed principle in machine learning. So it may have some meaning, right? So clearly one of the family or class of learning problem we get is supervised learning. And supervised learning started, I think around 70s or 80s, particularly in 80s when Leslie Valent began to formulate binary classification. And it introduced some very fundamental elements of data-driven basic learning. That is, the learner will receive IID samples from an unknown distribution, right? The keyword is unknown distribution. And then there's an unknown target function that's called labelers from a family of hypothesis class, right? So this is essentially how it's cast, right? So the input to the learner are the data space, its label, and hypothesis class, right? That's the common knowledge for learner. And then there will be unknown distribution, for example, modeling your emails. And the labeler could be whether it's spam or not spam from a particularly mechanism, maybe binary decision tree or some other mechanism to label it. And then there's a particular ground truth is there that allow you to produce so-called supervised data, namely data with labels. And essentially the learner began to receive this type of data. And then after computation, most likely optimization, we output a hypothesis that will generalize, which means you can predict the future data, right? So this data will be drawn again from this unknown distribution, almost like taking exams, right? So your exam problems are drawn from a similar type of problem, right? And this usually we call proper learning, namely you learn according to the hypothesis, but learning is more general. You can also learn improperly. And in fact, many of us learn improperly because it's painful to learn properly. You have to follow the rule of the teacher, which is I will come back to this issue. Improper learning means the student can build up any of the model they can generalize, right? There's no restriction on this. So this is the early days of Valent's work in 80s. And soon, clearly, in practice, people began to consider this classification-based learning. And one of the earliest examples for application is for the postal office try to recognize handwritings, right? So the label becomes slightly more complex, right? For example, just for zip code, you probably need 10 labels. And then with letters, maybe 50 or 100 letters. And then quickly, modern days, you get into infinite labels, right? Facial recognition, everyone is a label. So you get into this very quickly. A large data space, essentially, you can think about this infinite. The hypothesis class is infinite parameterized, maybe with finite dimension, and the label could be infinite, maybe with some kind of geometry. Okay, so this become broadly the schema, but the problem is still same. The only thing changed is the label, right? So this is usually called the multi-class supervised learning, right? So you like regression, everything can be recast in this language, right? The key part is unknown distribution, ground truth, and ID sample, and then you want to generalize. So there's a few fundamental concepts. And with this, one can begin to define this notion of learnability, that can you learn a concept from a concept class, right? And it's loosely just like what we think is that if you observe enough label sample, can you reduce your error is effective to zero, right? So that's the notion of generalized, right? And more concretely, it asks that if you have m samples, can you get error to epsilon? And usually m and epsilon has some kind of functionality, right? Like 1 over n, for example, could be other measurements. Okay, so this basically is the common language of supervised learning. Okay, and so there's some more fine detail. I will come back to this. There's some other detail of the model, but I will come back to this.
So the first one means that whether the model is learnable, learnable from no data to we have a sufficient data.
So yeah, so if you have sufficient data but finite, whether you can reduce error effectively. So that's the abstract notion. Yeah. The second one is more concrete measurements. You like students take classes. If you take 100 classes, can you get your score into 95 points, right? And if your students miss half of that class, maybe you can't, right? So that's called sample complexity, right? So, so number of classes you take essentially is a sample complexity. So supervised learning in principle basically is try to learn from labeled data and essentially try to build models for good prediction of future. And one principle I think is really important for learning is really encourage not to memorize, but to generalize. So I think that's a fundamental principle. It's not just try to memorize, right? Just like when we go to class, our job is not to remember the material, but somehow comprehend enough to be able to solve future problems, right? So this essentially follow very similar kind of connotation, and it has some other applications beyond just detecting spam. You can use it to model different type of learning phenomena, right? So ever since Valence began to formalize this notion of learning, then very quickly progress was made about characterized learnability, particularly in the 80s. Very quickly, this notion of VC dimension, I'm not going to overdefine it. I'm sure many of you heard about it and know about it. But you can just think of as a regular Euclidean space. You can think about the concept class to half space. In this whole talk, you don't have to think about anything more abstract, but you can just think about every hypothesis class called support vector machine, just half space. And the dimensionality is this Euclidean space, right? And your label function could be some other geometry. And they're able to say that in the binary classification case, this dimensionality, just like the Euclidean dimension, really capture learning. If that is finite, learning is possible. If that's infinite, it's impossible. So essentially, that result was proved. And with a very tight result on how many samples you need. The sample essentially is the dimension divided by epsilon in order. And the learning mechanism is also trivial, just optimization, right? So this is just like a classical first step of machine learning. Optimize to learn. And this result just completely captured that in the binary case, you don't have to think about anything else. There's no need for regularization. You just need to optimize to learn, right? Because it has a concept called universal convergence, right? So somehow uniform convergence. So somehow uniformly it converges. And but this multi-class one, when the label essentially can go to large and infinity, that characterization was only settled 2 years ago. So clearly it's much harder when the label become much more complex geometry. For example, label is in a high dimensional manifold, right? Or regression. It become much harder. And the proof, beautiful breakthrough, I think presented in Fox 3 years ago, used almost all the tricks, bells and whistles of the learning, compression, subset sampling, and eventually they managed to put together into a characterization of a dimension which is early defined that somehow also captured learnability. So the following basic question remain largely desirable. That is, this learning algorithm is so complex they produce. Do we have some kind of simple learning platform template that we can learn, right? Because from algorithmic design perspective, we like simple algorithm. Yeah, we don't like, for example, our field is filled with a fancy approximation algorithm. Nobody uses it, but mathematically they're so beautiful, but it's just too complicated to implement, right? But learning, again, is very similar to that, right? So the other simple platform, and some of the basic simple platform in people's mind still return to optimization or regularized optimization. So those are the front line of simple platform. So the question still return to whether you can using elementary way to shape your learning algorithm. And unfortunately, you can see how naive was our hypothesis 15 years ago. So after we mentioned our hypothesis in the coffee house, 2 years later, it's a beautiful result. And it was not quite magnified, but it just published. And in it, it has the following result, saying that in multi-class classification, that there are learnable problems that cannot be learned by any proper learner. So I personally really like the philosophy of this theorem. It's basically to say any teachers force you to write a proof in a particular way to learn their class. They didn't know the fundamental principle of learning. Sometimes you need to go beyond the taught hypothesis class to learn, right? Because there are certain things that you can't learn within its own system, right? You have to allow students to be creative enough to break through to learn rather than stay within, for example, if you're learning a decision diagram for a complex labeling problem, you cannot force people to using decision diagram to learn because in general, that just won't work, right? So this is a beautiful principle, but it's clearly against the hypothesis we had because regularized mechanism is a proper learning, right? Because we only say every hypothesis has a complexity. If you want to fit the model, you will output a hypothesis that is from the class, right? So that essentially disproved this naive conjecture wishful conjecture we had. We're not trying to make the most smart conjecture at that time. I think likely it's wrong. So indeed it was wrong, right? But it did make, just like a research, right? Anytime you see a counterexample, it's really the moment to think again, right? Rather than to say, oh, I'm so off. And then one of the questions clearly is that what is the minimal change to regularization? What more information you can give to regularization in the smallest manner that capture learning, right? I think this philosophy continue to be a good hypothesis, right? So what additional knowledge your regularizer need to learn to know in order to learn completely, right? So that's essentially become the next driving questions from the research. And so our first attempt is to make the regularizer to induce improper learner, right? Because improper learning is off. So you have to have a mechanism to create improper learner. And this actually mathematically is very simple. Because what is proper learner is you have a family of function, you will choose one to approximate. mathematically. But mathematically has other concept long ago people use called a piecewise function, right? You can take a family of function, and here you use one piece, here you use the other piece, and in all the settings, people spline them together, right? They're not just connecting them, they make them high order smooth, right? So all those things are called improper learning, right? Because you're not learning with a piecewise linear function. It's not linear function, right? It's a much bigger, and also we knew it, piecewise linear function is almost universal to approximate, right? The whole finite element method, all those things eventually went for that type of improper approximation of the functionals, right? So here is similar too. Maybe one can use so-called local regularizer, namely the regularizer not only look at the particular hypothesis, but also look at which point you want to predict to indicate which hypothesis is simple. So for example, a hypothesis could be very complex here, then suddenly become linear here. And the other hypothesis could be very complex here, become linear there. Then if you need to solve a problem here, the red is simple. But if you want to solve an orange one, the orange one is simple, right? So the hypothesis could be in terms of how simple they are, depend on where you want to solve your problem. So that's clearly one of the first naive way to think about piecewise and this improper learning. And so then indeed we try to build regularization this way. We try to prove maybe this will be universal, right? So this is our second naive conjecture. And unfortunately, the 14th proof is so powerful. After we twiddle it just a little bit, we realize this is also false, right? So which means a slightly more intrinsic reason just of being improper. So even though we induce an improper family, look like kind of locally adaptive, we call local regularizer, and it still didn't sufficiently capture learnability. Okay, so then we began to see what other data we can put in, and this actually connected us with a more classical learning framework now, right? This more classical learning framework is called we don't need this slide now. It is called unsupervised data, unlabeled data, right? So when you ask people in practice, you say, what your data look like? They often classify the data into two classes. Unlabeled data, they said we have abundant of them. Just like our email, we have a lot of emails. Mostly are not labeled spam or not spam. And then we have some labeled data. So usually it's more expensive to receive labeled data because someone has to do the work to label, and sometimes people pay for the label. But unlabeled data are often more broadly generated. Right? So that's why in this kind of framework of learning, then the unlabeled data quickly also become our next target to say, can we actually utilize, how do we utilize unlabeled data? And maybe one way to utilize unlabeled data is not go through the classical clustering and this type of thing, but maybe just intrinsically try to build a regularizer. The question is whether we can do that, right? So this essentially coming into as our framework. So namely, we want to build a regularizer that derive both from the data and also some of the unlabeled data. Suppose you give me data without label, then give me a label. So you treat the label as into data generation as two-phase, right? People give you the data, then some people come there to label it. So then you want to do something beforehand, okay? And there actually, we managed to make the proof to say you can capture learning. And with a factor of loss 2 of the sample complexity. I'm not going to talk about this one. I'm going to talk about the more optimal one. We said if you allow randomized learner, namely a learning algorithm that return a distribution of the hypothesis, that when you need to solve a problem, you just use your own distribution to sample one to label. And this is called randomized learner. And you can actually achieve optimal learning using the regularization framework in this language, and completely fit with the optimal sample and optimal learning error. So there's no gap anymore. Okay. So this is essentially the main readout I'm going to present, and some of the structure that we utilize. Okay. So to do this, let me iron out a little bit of this model for learning. And there are several ones. The valiant one is called pack learning, which is more widely accepted. And there's essentially equivalent to the one, mathematically more clean, at least in my perspective, was proposed by Vapnik, like V or VC dimension, in the early 70s. And so this one may come a little bit more closer to Soviet education. And just like every model comes from practice, this I feel like, my father used to study in Russian-based, Soviet-based university, and he always explained to me, he passed away now, and he explained to me about the harsh oral exam and the variety of their exam. And when I read this model, it sounds like the voice of from the school. So it gives an interesting way to think about what is hypothesis class, what is learning, or what is preparation. All those concepts showed up here. So this is called transductive learning, right? Transductive learning go basically as following. The teacher adversarially choose data points. You can think about data point as a problem. And you can think about label a solution, right? So in this discussion, it's easier to think that way. Problem and solution. Solution are label and problem are the data points, okay? And then clearly students don't care about the problem or solution. We care about the exam. So you have to define what is the exam, right? So the test will at that time choose a random of this problem to be the test problem. And then basically the teacher will give the solution to all other problems, right? So essentially, this one, first, what is hypothesis? Hypothesis is just a collection of books. This book is a encyclopedia books written by different people, different beliefs. And in this encyclopedia book, they have all the problem of universe and all the solution of it. And the book then have to be consistent, right? Because every book writes their own problem and their the solution to according to their belief to the problem. Okay, so that's called the hypothesis class. Hypothesis class is just a pile of books. Okay, so because that is public knowledge, you can think about the first day of teaching. The teacher came, carry a pile of books, and just lay on in front of you to say, in this class, I'm going to teach one of the book. Which book? I'm not going to tell you. That's called the ground truth. So the ground truth is just one of the book, right? Just one of the book that label give you solutions, right? So the ground truth is just one of the book, but teacher never told you which book is teach. And then the teacher also on day one just offer you all the problems it will consider in the class, right? So M of them or M plus one of them. And then it will say, okay, finally I have to test you. And I will be very fair, professor. I will choose a random one. So you just go there, choose a random problem, and take a random problem, just put on the table. Say, this will be the exam, right? On day one, you know the exam problem on day one. And so then what is teaching? The teaching will teach every other problem, one a day, right? It's just like in Russian teaching. On day one, the teacher doesn't even look at you. They take one of the problem, copy on the board, and then proof. And you just write on the board, then teacher turned around and walked away. Right? No interaction with the students, right? It's just, I'm sure you have such teachers too, right? Never look at it. Just write all the problem, write all the proof, up, down, they just gone, right? And then basically students just sit there day after day, watch a problem written there, a proof given. And the teacher every night has this particular book in the pocket. When they go home, the teacher, what is called to prepare for the class, is to memorize the proof. Right? Just memorize the proof. That's how a teacher teaches. Okay. When you become professor, don't teach it that way. Look at your students. So then basically day on day after M days, you're done teaching. And then the professor said that's exam time, and it will put this one as an exam. Then students at that time, with all the knowledge of all the books, the M of the problem and their solution, I need to solve this problem, right? And they knew it's in one of the book, right? They knew it's in one of the book. So in some sense, they have to figure out that book and copy it. Right? That's called learning. Right? It's learning is essentially is trying to detect which book it has. Okay, so this is equivalent in this transductive model. Right? So this transductive model is connected with packet learning with I think about log factors of sample complexity. Okay, so but this one is nice is because it's connected with the graph theory. There's a graph theoretical characterization of this framework, and it goes as following. So you can build a bipartite graph. So this is called what is preparation for students, right? We all encourage our students to prepare your class before you take one, right? So on day one, you have all the books, you have all the problems. The student can prepare. And imagine students indeed have infinite amount of time. Instead of playing games, you read all the books and look at all the problems, right? And I'm not saying this is so far efficient. I'm only trying to prove the existence of regularized learning. So currently, my proof is not constructed. It went through a mathematical proof, right? So the preparation goes like the student just began to read all the books and label all the problems, right? So each book will label the problem. So this you can be, it doesn't have to be 0, 1, could be other solutions. So each book clearly solve all the problem, each book, all the problem, right? And then on this side, you can imagine what might be the lecture from professor, namely when one of the problem is missing, and you're using this book, you will teach it this way. You can actually emulate all your professors because the professor never talked to you. You can just write out all possible professors, right? And the book of their choice. So you can define this as a bipartite graph. So what is exam time? Exam time is finally a professor taught something, then you knew which entry the professor taught. And then it will face some of the book that is consistent. Then you have to choose one of them and to give you answer, right? So basically, student learner is just choose a matching from left to right. That's just what learning, that's all learning is, choosing from left to right. And so learner basically will do assignment from left to right. And you can see all the degree here is equal to sample complexity because it's corresponding to one of the problem was using as a test, right? And so what is the performance of students? Because professor, they usually want to mess up students. So they want to choose the book that you feel the most against a learner. So which means the learner want to miss as less book as possible. So the score is the maximum missing in one of the nodes. So that is so basically the learning with epsilon rate means that everybody here receive a degree 1 minus epsilon fraction of degree. Then you can consistently answer questions. So this is completely captured by this matching problem. And this matching problem, if you take the best epsilon, that's define the optimal learning. You can essentially using this to prove that. And so once in computer science, if you see a matching, the next thing is a linear program, right? Because matching, like max flow min cut, they are captured by convex programming, particularly linear programming. So you can write down the linear program of all the possible paths. Imagine you already know the optimal learning rate, epsilon star. Because here I try to prove for existence, right? I assume I already know the learning rate. And then basically you can use PM to be a probability of choosing any passing students. There's different students prepare differently, and you just produce a distribution of those students. And in our program, we maximize the entropy of all the passing students, right? We define what is qualified students, and we define their distribution. So this is the program we write down. And we began to analyze this linear program. So essentially, the whole result came from the structure of this linear program. And this program, one thing nice, because of this max entropy objective function, you don't have to read too much detail because sometimes every proof has a little bit more detail, but I want to get the highlight intuitions through. Is that, so this program is nice, it's essentially strongly feasible, which means essentially the optimal solution is essentially unique. It has strong convexity and it has a nice, well-defined optimal solution. So usually for linear program, usually we don't only look at the solution of linear program. Very often, more importantly, mathematically, is to look at the dual solution. So what are the dual solution? Solution is all the matchings. The dual solution actually are numbers on the hypothesis. Each hypothesis, right? Each hypothesis gave a dual variable. So you can actually get the projected solution for the hypothesis. And the one thing nice of this convex program, essentially mathematically, the whole argument is that when you look at the dual variables, they're all non-negative. So that's actually one very important property. The dual variables are non-negative. So why non-negative numbers, collection of numbers, non-negative is important? Because essentially they're distribution. You can normalize into distribution, right? Because distribution are the bunch of non-negative numbers add up equal to 1. So whenever in modern days statistical or learning theory, the moment you have non-negative numbers, they are distribution. That's essentially the mathematical structure. So here, basically, after we solve this linear program optimally, and that the dual solution defines distribution on the right-hand side of the image, right? So which means that they define a distribution of the book or hypothesis, right? So this is the distribution a student guessing the professor, right? Remember, the professor give you a bunch of book and they give you a bunch of problem, and the good students just study this and began to guess the book, right? I'm sure in high school, some of you facing standard tests. When you couldn't solve a problem, you did the same thing, right? You try to guess the intention of the problem rather than you try to solve it, right? You got multiple choice, right? So you want to, right? So this is in the same way, right? Once you look at the problem, you begin to understand your professor. And this program just doing that. So namely, once you have this unlabeled data with the hypothesis class, you already have some kind of belief that this is what my professor might behave. And this is called preparation. You prepare your class by guessing your professor, right? So once you guess your professor, this induces what we call the Bayesian learner, which is also one of the universal family often used in machine learning, particularly when information given to you incrementally. I'm not just saying online learning; it's batch-based. So essentially, the Bayesian learner is that the moment you observe data, you just build your belief of the hypothesis, and then you get more data, you just update your belief, right? So you go from prior to posterior. So you continue to do this prior to posterior update of a belief. This is called Bayesian learner. And I think a lot of machine learner believe Bayesian learner is universal, because what else to learn is building beliefs of the observed data, update when you see new one, and ultimately you have nothing to update. It must be the best way to learn, right? So this also believed to be a universal schema, and so this learner essentially did exactly this way, right? So namely, first this unsupervised phase. I build this graph, solving this linear program. I got a distribution on the hypothesis. Then the teacher taught. This is supervised phase. Then you just update it into another distribution, right? Because some of the books are eliminated. Of all the survival book, you just project the distribution. It's just that simple. You just eliminate all inconsistent books. That's exactly what we take GRE TOEFL, right? Anything inconsistent, you just knock it out. What else you can do in the rest of this answer? You have to choose one, right? You usually use your own prior belief, project into their choose one, right? Use your instinct to choose one. So this is exactly the same way. And then when you need to solve, you run this new distribution and find the book and just write down the copy down solution. So this is the Bayesian learner, right? The unlabeled data preparation time, you get a guessing distribution prior. Then you supervise learning, you update your distribution, eliminate anything inconsistent, and exam time, good luck, right? If you're left with one book, you solve it. If you're left with 3 books, you have some probability to solve it, right? So this is exactly this learner. And this program actually proves this is a universal learning mechanism for supervised learning, right? If it can be learned with certain rate. This will learn optimally. Right? Not clear how efficiently you can do, but at least mathematically, it allows you to learn optimally. So, so this is the Bayesian one. And then once we began to analyzing Bayesian one, I'm able to return to my original problem. That is, so when you do from the step 1 to step 2, the difference is really usually called KL divergence of these two distributions. And this KL divergence is just like a linear, like Taylor expansions, the first order. It's really something plus something. And this KL divergence is just a plus something. And that is regularization. Right? Because something plus something you minimize. So this is exactly that term come out. So this proves that the unlabeled data can be used to build regularizer. And when you need to solve, you just optimize it. So this actually proves the conjectures we eventually come to. So this shows that this local regularization using unlabeled data is sufficient to learn for supervised learning, right? So Bayesian is universal, and this is also universal. And it's also connect to our principle. Sometimes in learning, people also use called max entropy principle. That is, if you have many possible solutions, don't just knock out the one. And still, you need to consider all the possibilities. Because don't make assumption. Don't make assumption is algorithm. Right? If you make too much assumptions, then you introduce complexity to the hypothesis. So if you don't make an assumption, it's algorithm. So this essentially this program we feel is quite intrinsic linear program, at least to capture the multi-label supervised learning into just one framework. And the third part is not effective because we don't know how to build this thing in polynomial time, right? So those are our continuous investigation right now. So to conclude, you can see a random conversation, a random question and answer sometimes can introduce a research problem. I think particularly for students that on one hand, it's nice to have good advisors to give you good problems. And sometimes it's good to venture a little bit to some random curiosity questions and make you wish for conjectures, try to explore a little bit. And then sometimes you get deeper and deeper into your exploration. And a lot of times, somehow, it will at least drive you towards certain direction of interest. Right? I'm not sure it can always be fruitful because most of my exploration end with nowhere, right? I feel like my career as researcher, most of the time I failed, right? Walk, then nothing happened. Then you have to go back to try this process again, and finally ask some senior mentors to say, well, why don't you tell me a problem? I need to think a little bit more, right? So, but I think it's a mixture of exploration and build upon some of the wisdom of the past scholars, right? So this gives us this adventure into the land of regularization of something clearly we started without overly conceptualized. And this, we at least feel we gain some understanding, particularly on unsupervised data. Right? I feel at least it's an interesting angle from my own perspective. Right? And so this gave us a small step template, a step towards an algorithmic template, because we did regularize a little bit of the learner, and currently it is still just too inefficient. I'm still looking for maybe some other algorithmic mechanism to speed this up. And so it did lead us to some other research. I'm not able to talk in this lecture. And we did identify some other conjectures along the way, which eventually become quite mathematically interesting, particularly considering learning in the model with uncountable or infinite data space hypothesis and label. And apparently some of those questions was not natural one, not formally addressed. And they all come out reasonably naturally in this study. And And just like everything else, it creates a lot of open questions once you have one. Particularly in our cases, how much of the unsupervised data you indeed need. And one of our basic hypothesis actually was solved by a 17-year-old in high school. Somehow he gets stumbled on this conjecture and he managed to solve it and get into code, I think, this year. Yeah. So there's a talent everywhere, and some of those does create will define enough problem. Thank you.